Ever wonder what holds the entire universe together? I mean, really, at the most basic level. At the heart of every single atom, you've got this tiny, super dense core called a nucleus. But here's the thing that's puzzled scientists for a long time. Why are some of them, like the lead in your pencil, just rock solid for billions of years, while others, like uranium, are basically ticking time bombs, constantly falling apart? So, today, we're going to dive deep into that. We'll start by uncovering a set of magic numbers that seem to give atoms superpowers. Then we'll look at the early models that tried to explain this, see how these same rules build stars, and finish up right on the cutting edge with a brand new nuclear mystery that has scientists scratching their heads. All right, let's get right into it. What's the secret sauce for stable atom? It all starts with the fundamental puzzle right at its core. Now, this isn't just some random trivia question. The answer is fundamental to why the universe even exists as we know it. And it all begins with a really strange, almost, well, magical pattern in the numbers. Let's just take lead, for example. Its nucleus has exactly 82 protons. And that number, 82, is special. It's not random at all. It's like a cheat code that makes the lead nucleus incredibly stable. And it's not the only number like this. Early on, physicists noticed this wild pattern. Whenever a nucleus had 2, 8, 20, 28, 50, 82, or 126 protons or neutrons, it was way more stable than its neighbors on the periodic table. They literally called them magic numbers because the effect was so strong, and for a long time, nobody knew why. And check this out. This graph shows you just how powerful this effect is. It's basically showing how likely a nucleus is to grab a neutron that's flying by. And look at those massive dips. They happen right at the magic numbers. These nuclei are so stable, so content, that they just let extra neutrons fly right on by. Okay, so what could possibly be causing this magic? Well, the very first major attempt to explain the nucleus was, beautifully simple. Back in the 30s, brilliant minds like Niels Bohr imagined the nucleus was a lot like something we see every day, a tiny, charged droplet of liquid. Just picture all those protons and neutrons jumbled together, kind of like water molecules in a bead of water. The idea was pretty intuitive. It assumed the nucleus was a sphere, it had a constant density, and the particles inside were really only pulling on their immediate neighbors, which creates something like a nuclear surface tension. It made a lot of sense. And you know what? For explaining big, dramatic events like nuclear fission, this model was amazing. You can just picture it. A neutron comes in and hits this drop. It starts to wobble and stretch out, and then, snap! It breaks in two, releasing a tremendous amount of energy. But here was the problem. The liquid drop model was fantastic for the big, messy stuff, but it treated every proton and neutron as basically the same. It had no way, absolutely no way, to explain why these specific, magic numbers created these little islands of superstability. The model was clearly missing a huge piece of the puzzle. So, to find that missing piece, physicists had to look even deeper, down into the weird world of quantum mechanics. And that's where they finally found the real answer. The big aha moment came when scientists stopped thinking about the nucleus as a chaotic liquid drop and started picturing it as a highly organized structure. Think back to chemistry class. You know how electrons fill up those nice, neat shells around an atom? Well, the idea was, what if the same thing was happening inside the nucleus? So in this new shell model, protons and neutrons don't just clump together randomly. They fill up distinct energy levels, or shells, one by one. And here's the kicker. When a shell gets completely full, the whole nucleus becomes incredibly stable and tightly bound. And guess how many particles it took to fill those first few shells? You guessed it, 2, 8, and 20. The first magic numbers suddenly made perfect sense. It wasn't magic, it was quantum mechanics. But wait, the simple model still didn't get the higher magic numbers right. There was one last secret ingredient, a purely quantum effect called spin-orbit coupling. It's basically a tiny interaction between a particle's spin and its orbital path. But that tiny interaction was just enough to shift the energy levels around, and with that final tweak, boom, the shell model perfectly predicted every single one of the magic numbers. The mystery was finally solved. So, Great, we've cracked the nuclear code. But what's really amazing is that these rules don't just exist in a physics lab. They actually shaped the most massive and extreme objects in the entire cosmos. First, let's use what we've learned to bust a really common myth. You've probably heard it a dozen times. Iron is the most stable element. It's the final ash of stellar fusion. Well, as it turns out, that's just not quite right. If you actually plot out the binding energy per particle, which is the true measure of nuclear stability, the real winner, the king of the hill, is actually nickel-62. It just squeaks past iron. Now, iron is way more common in the universe because of the specifics of how stars burn, but if we're talking pure, rugged stability, nickel-62 is the undisputed champ. And these rules of stability get pushed to their absolute, mind-bending limit in the craziest places in the universe, the hearts of neutron stars. We're talking about the collapsed cores of giant stars, where matter is crushed to a density that's literally hundreds of trillions of times denser than anything on Earth. Inside these stars, the pressure is so immense that nuclei can't even stay in their nice little spherical shapes. They get squeezed and mashed together into these bizarre configurations that physicists, with a great sense of humor, have nicknamed nuclear pasta. You get blobs that look like gnocchi, long strings like spaghetti, and even giant sheets that look like lasagna, all made of pure nuclear matter. And here's where it all connects in a way that just blows my mind. The same exact physics that determines how thick the neutron skin is on a single lead atom here in a lab, that same physics also dictates the size of an entire neutron star. Just think about that for a second. By measuring a single atom, we can predict the size of a star thousands of light years away. That is absolutely incredible. So you might be thinking, okay, story's over, we figured it out, we can connect atoms to stars, but well, it turns out the nucleus isn't done with its secrets just yet. Just very recently, scientists doing experiments at Los Alamos found something that, according to our best theories, simply shouldn't be there. In situations where the shell model predicts complete randomness and chaos, they found repeating, predictable patterns. This is a huge deal. It's a flashing sign that our understanding is still incomplete, that there's brand new physics hiding inside the atom. So think about this journey. We started with a simple question about why some atoms are stable, and that led us to create models so powerful they can describe the physics of stars. But just when we thought we had it figured out, the nucleus surprised us again. We peeled back one layer of the mystery only to find a deeper, more complex puzzle waiting inside. We know what holds matter together, but the real question now is, what secrets is it still keeping from us?